Good afternoon, dear children. Our next topic is quality factor. We have studied about LCR circuit, and this is a particular term coming in LCR circuit. So here, first let us see the graph between frequency and the current. We know that in LCR circuit, the current depends on the impedance, which again depends on the frequency of AC. So here omega is here, that is a frequency, and current is marked on the y-axis. We know that for a particular frequency omega r, which is known as the resonance frequency, the impedance of the circuit, that is effective resistance, becomes minimum and maximum current flows in the circuit. So for a frequency omega r, the current flow becomes maximum. That maximum current is I0, which is known as the peak current. Now we have another current, which is the RMS current, which is this peak current I0 by root 2. So from this graph you can mark I0 by root 2 here. So check what is I0. It's 1 by root 2. That particular value of current has two frequencies here, omega 1 and omega 2. Those frequencies for which omega 1 and omega 2 we get the RMS current. So this omega 1 and omega 2 are equally separated from this resonant frequency by a small amount, delta omega. A small frequency difference will be there, delta omega. So this total frequency range from omega 1 to omega 2, we get a current flow which is at least equal to the RMS value of current. This range of frequency is known as bandwidth. This range of frequency is known as bandwidth. So this bandwidth is delta omega plus delta omega, that is 2 delta omega. So this is the upper frequency and this is the lower frequency for which we get the RMS current. So this bandwidth 2 delta omega is equal to omega 2 minus omega 1. From that we can rearrange this omega 2 and omega 1, we can separately write. Omega 2 is omega r. Here you see omega 2 is omega r plus delta omega, and omega 1 is omega r minus delta omega. Now this resonance frequency omega r, if you divide it with the bandwidth, that is omega 2 minus omega 1 or 2 delta omega, both are bandwidth. So this resonance frequency divided by bandwidth we call with a name that is known as Q factor or quality factor. That is our today's topic, Q factor or quality factor. So it is nothing but the ratio of resonance frequency to the bandwidth, that is omega r by 2 delta omega or omega r by omega 2 minus omega 1. Now we have this equation, the maximum current and the RMS current are related as I is equal to I0 by root 2. So when I is I0, in the circuit when the current is I0, that is possible when the impedance is equal to resistance R, which means only resistance can offer a opposition to the current. So that time current maximum flows, that is I0 is, suppose E0 is the voltage, maximum voltage divided by R. All other situations the current flow will be E0 by Z. Z is a total effective resistance. So only when Z becomes R alone, then current becomes maximum I0. We know I and I0 are related by I0 by root 2. So if I is E0 by Z and I is I0 by root 2. We can combine that and we can write I0 by root 2 is equal to E0 by Z. That I0 also, this I0 we write as E0 by R. So E0 by R root 2 is equal to E0 by Z. Z is, we know in LCR circuit, Z, the total effective resistance is square root of R square plus L omega minus 1 by C omega. So that omega is the frequency for which the current becomes I0 by root 2. So that omega can be omega 1 or omega 2. So here omega can be omega 1 or omega 2. In both cases current is I0 by root 2. So let us substitute omega 2 as a frequency omega 2 because the current has become I0 by root 2. So I0 by root 2 is E0 by R root 2, E0 by Z, Z is this, and there we have given omega as omega 2. We can even substitute omega 1 also, no problem. So from that equation, if you this E0 cancel, we get R root 2 R. Here R root 2 will remain and this term, the whole square. Now you can square this equation, it becomes root 2 square, root square is 2, R square is equal to square root of this term, its square. So R square plus L omega 2 minus 1 by C omega 2 the whole square. From that equation we get R square is equal to L omega 2 minus 1 by C omega 2 the whole square. Or we can get R is equal to L omega 2 minus 1 by C omega 2, this equation. Now already we had equation for omega 2 was omega R plus delta omega. Initially we told omega 2 is omega R plus delta omega, that also we substitute here. Now from this we can take omega R outside. Here we have omega R. So when I take here outside from this term, here it becomes 1 and there is no omega R here, so we give a omega R in the denominator. So that when I take it inside, omega R into 1 becomes omega R into delta omega by omega R, that becomes a delta omega. Because when it enters the bracket, omega R cancel. Here also I do the same. Now look at this term, the second term. Here I have in the denominator 1 plus delta omega by omega R. This is in the denominator, so I can take to the numerator by bringing a negative power 1. I can write it in the numerator with a minus 1 power. That this C omega R is already there, that is written here itself, no change. And already we know that at a resonance omega R we have the condition for resonance. Omega R is equal to 1 by root LC and 1 by omega R is equal to root LC. We have these two relations. That we substituted here. Omega R here, that is replaced as 1 by root LC. And here we have 1 by, this is in the denominator, so 1 by omega R, that is root LC. So it becomes in the numerator root LC by C. So here 1 plus delta omega by omega R whole to the power minus 1. So this term, this comes under binomial expansion. This is in the format 1 plus x whole raised to n. In that case we get 1 plus nx. Extra terms will be there. So what we do is, for this special case, as delta omega by omega R is a very small number, this becomes 1 minus delta omega by omega R. Now here is another term, L into 1 by root LC. This L I write as root L into root L. L can be written as root L into root L. If so, 1 root L will cancel here, then it becomes root of L by C, square root of L by C. This is root L into root L by root L into root C. So L, root L and root L cancel. Numerator 1 root L will be remaining. So remaining terms here also root LC by C. This C we can write as root C into root C. Then it becomes this root C and 1 root C cancel, root L by root C will come. That is written together here, root of L by C. No other change. And in both terms we have root L by C that we take outside here, 1 plus delta omega r and a minus of 1 minus delta omega r. This minus into 1 minus 1 minus into minus plus delta omega by omega r. Now this 1 and minus 1 cancel, delta omega by omega r, delta omega by omega, 2 times delta omega by r comes. Now this term, which is the ratio of here, which is the ratio of resonant frequency to the bandwidth. Already we told Q factor, which is the ratio of resonant frequency to the bandwidth, omega r by 2 delta omega. This we get as 1 by r root L by C. Take this r here, it becomes 1 by r, and this term comes here, omega r by 2 delta omega. So this term is called a quality factor. It can also be defined in terms of voltage, but we do not need that much derivation. It can also be defined as ratio of voltage across inductor or capacitor at resonance to the applied voltage. That is also possible. We do not go for that. We need this equation alone. That is enough. This LCR circuit has a particular application called a tuning circuit. Here we know that in LCR circuit maximum current flow takes place when L omega is equal to 1 by C omega. That means for a particular frequency, by adjusting the value of L and C, we can control the circuit. That means for a particular frequency in LCR circuit, we get maximum current flow. That is our resonance condition. So for receiver signals, like the receiver in your radio, you have a knob. When you rotate the knob, you are actually adjusting the capacitor value. So by adjusting inductor and capacitor value, we can receive particular signals. This is actually tuning circuit, the working of tuning circuit. So for a particular Q factor when it is large, or bandwidth is small, when Q factor is large, bandwidth will be small. The receiver is a good circuit for that particular frequency. So if you have two circuits whose current versus frequency is given here you can see X and Y. So the circuit X has a particular sharp resonating condition. So circuit X will be selected for tuning the frequency omega r, because for that particular X curve Q factor is very large compared to Y. Otherwise we can say the sharpness of resonance is high for X than Y. So it's just an application, like we are using it in LCR circuits, in tuning circuits.